पीछे एक मल्टी प्रोटोकॉल label switching, right? See, we are calling it multi-protocol, which means MPLS is going to be an open standard, right? Open standard. It can support IPv4, IPv6. I mean everything. It can encapsulate everything actually, right? It can encapsulate your layer 2 traffic. Can encapsulate layer 3. It will be depending on whether you configured MPLS VPN as layer 3 VPN or layer 2 VPN, right? But it's a multi-protocol. It supports multiple protocols, you can say. We are calling it label switching, which means MPLS is quite different, because here we are saying label switching, which means that it will perform switching based on labels. It's not gonna to perform switching based on IP addresses, right? And actually, if you talk about the traditional switching method is what? IP switching. Till now we are using IP switch. Like what happens usually, let's say this is router 1 and this is router 2. Whenever a router will receive any packet, it will learn its destination IP address. It will open its IP header, will open IP header, and also will read its destination IP address and will perform lookup for its destination IP address, right? And then will forward accordingly, right? What is the problem with traditional switching? Nothing. We are still using SAF, Cisco Express Forwarding, right? And SAF is quite fast. It's a fast switching, right? Then what is the uses of this MPLS? See, although SAF is fast switching, right? Cisco Express Forwarding, it is performing express forwarding, but still, some problems are there. Even if SAF is switching, SAF table is switching your packets, but still it is opening IP header. It's not it. An IP header is a 20 bytes long header. Each hop, each router has to open 20 bytes long information, and then how to perform lookup in its fib, which is kind of SAF table, right? Which is SAF table. And it has to perform lookup in its SAF table, and then accordingly it has to switch packet, right? So even if we are using SAF, but still all routers, all devices have to open IP header of received packets and have to perform lookup in their SAF table, and accordingly they will switch that packet, right? So even along with SAF table, we still require to open IP header. And if you are opening IP header, if you are looking for destination IP in your routing table, in your SAF table, which means that all core routers must have all routes in their routing table, because SAF is a replica of routing table. If you are having 1 lakh prefixes in the routing table of routers, and if you are having like 50 core devices, 50 core routers, which means that all those 50 core routers must have all those 1 lakh prefixes in their routing table. And to maintain 1 lakh prefixes in their routing table, it will require huge memory and higher CPU cycle. Are you getting my point? That was the biggest issue in older networks. And this SAF came due to this MPLS only. Without SAF, you cannot think for MPLS. MPLS cannot work or cannot be configured without SAF. Now it's not necessary for me to explain you SAF, that how does it really work, because I have already explained it to you in very good manner. Like how many types of tables are there, why do we require Ceph, how does it operate, I mean how does it work, how does it function, and all these things, right? So everything I already described it to you in the beginning of the classes, right? So for MPLS, Ceph will still mandatory, right? It is mandatory for MPLS, right? So this MPLS has this capability by which it eliminates that requirement to open IP headers on each and every hop, because we are calling it label switching, which means that it will be performing switching based on labels, right? So it will not require to perform traditional switching now, which means that it after implementing MPLS onto core devices, now it will not require to open IP header on each hop. They will simply open label, and based on labels they will switch that data. And here, because I'm saying that it is not required, or it will not require to open IP header on each and every hop in the core network anymore, which means that it will not require to have all prefixes available in their routing table. And that is why we are saying that MPLS has made core as BGP free core. You will require to implement BGP only on edge devices, not on core devices, right? So in MPLS, what happens actually, you must remember that MPLS exists in between layer 2 and half, right? I mean in between layer 2 and layer 3. MPLS works in between layer 2 and layer 3 here. That is why we call it layer 2 and half protocol. If someone asks you that on at which layer of OSI model it works, so you will simply tell that MPLS works at layer 2 and half of OSI model. Right? How does it work? Just try to understand with this example. Let's say this is router 1. This is router 2, router 3, and router 4. This is 10.1.0/24, and this is 12.1.1. This is 2. This is 23.1.2, and this is .3. 34.1.3, and this is what .4. Let's say this is S0 by 0, and this is S0 by 0. This is S0 by 1, and this is S0 by 0. S0 by 1, and this is again S0 by 0. Understood? Fine. Now let's say, and one more thing, these labels are not these are not different thing actually. These are simply decimal numbers. Labels are simply decimal numbers, and I think these are 32 bits long, not 32, 20 bits. Labels are 20 bits long. Label numbers will be 20 bits long numbers. right? So I think 2 raised to 2 exponent 20 would be something like 1 lakh or something like that. You can calculate it by yourselves. That will be range of labels, right? So let's say that R1 is giving this prefix to R2, and we are assuming now that MPLS is running in this network, right? So R1 will generate, let's say it has generated a label 10 for this prefix, right? So it will be giving this update to now R2, that if you wanna reach 10.1.1.0/24, then your next hop is going to be 12.1.1. exit interface is going to be S0/0, and because it received R2 received this prefix from R1 with the label 10, so outgoing label, right? Because it received with it, right? Outgoing label is going to be now 10, because it received this prefix with the label number 10. That will be known as outgoing label. Remember that whenever a device will receive any label with any prefix, that label will always known as outgoing label, right? Then it will generate, see, labels are locally significant, right? So R2 will generate its own label for this prefix now, right? So that will be known as local label now. For R1 its local label was 10. For R2 its local label is going to be now, let's say, 20. And now R2 will give this information to R3 that if you want to reach 10.1.1.0/24, then your next hop is going to be 23.1.2, and exit interface is going to be now serial 0/0. Outgoing label is going to be now you understand, 20, and local label is going to be now, let's say, 30. Then R3 will be giving this information towards R4, that if you want to reach 10.1.1.0/24, then your next hop address is going to be I think this is 34, right? 34.1.3. exit interface is going to be serial 0/0, and outgoing label is going to be 30, and let's say local label it have generated as 40. You understand? So whenever any packet wants to reach now 10.1.1, let's say the destination IP of a packet is 10.1.1.1, right? So R4 will forward that packet towards R3 with the label number 30, because outgoing label was 30. Now whenever R3 will receive any packet with the label number with the label number 30, it has this entry that it will be swapped with 20, and it will be forwarded out from S0/0. So it will not require to open its IP header anymore to learn its destination IP address. It will open simply this label, right? Then this R3 will perform swapping. 30 will be swapped with 20 and will forward this packet out from serial 0/0, and will forward this packet towards R2. R2 will receive it with the label number 20, and 20 will be swapped with 10 and will be forwarded out from S0/0, you see, and finally packet will be delivered on R1. You understand? So in this manner, see, this is the beginning, this is the basic idea of that how MPLS how MPLS works. This is not the exactly way that how MPLS works, but I'm just trying to make you understand that how will it work actually, right? This is not the exactly way, because in future I will be teaching you that okay, this is the exact way that how MPLS works, but in somehow it works something like this. It will be switching packets based on label numbers, right? And labels will be allocated by devices itself, and labels will be having local significance. Understood? Is there any problem now in it?
So on router
Required to open IP header anymore, and they can switch your packets based on labels only, right? And labels are very having very small size, like they are simply 4 bytes long labels, only 4 bytes. So previously each and every hop was required to open 20 bytes long information, but this time they will require to open only 4 bytes long information to switch your data based on labels. So that is why MPLS is more popular, or you can say MPLS is more beneficial to implement in networks, in today's networks, actually, you can say, especially at the end of service providers. Because just think about that, like if you are a service provider and you are having like 50 routers in your core, and there is no MPLS, so on each and every device they have to implement BGP, and all devices have to have full BGP table in their full BGP table, right? Otherwise they won't be able to switch your data. So basically that requirement has been eliminated by MPLS. Now they are simply required to implement BGP only on their edge devices, right? So this is the most you can say yes, most advantageous thing of MPLS, that it has defined your core as BGP free core, right? Along with that, with using MPLS, you can also implement layer 2 VPNs. Like previously we were implementing Q in Q tunnel, right? Nowadays Q in Q tunnel is not popular, right? We do not implement Q in Q tunnel. Reason being, like Q in Q tunnel is something like layer 2 VPN, right? But in that, actually some VLANs, I mean metro VLANs were required in that, and for each customer it was mandatory to use a dedicated VLAN by service provider, right? So that was the biggest disadvantage of Q in Q tunnel. So later on they implemented layer 2 tunnel in MPLS as well. So we will also implement MPLS layer 2 VPN along with layer 3 VPN, right? So I will show you that how can you form layer 2 connectivity in between two remote sites with using MPLS, right? Fine, forget about that. Let's start this MPLS once again, and for that let me use so there will be some terminologies that is mandatory for you guys to understand, right? First of all, and then yes, what is that? Just go through it. Routing protocols are used to distribute layer 3 routing information. Forwarding decision is made based on packet header and local routing table. Routing lookups are independently performed at every. This is the traditional IP routing, right? And the exception case is what? Only PBR. This is traditional IP routing. This is the network. Update given to this router, then this router to this router, packet came from which wanna reach that particular prefix, so it will perform routing lookup, then again it will perform routing lookup, then again it will perform routing lookup. Every router may need full internet routing information. Destination based routing lookup is needed on every hop. Then MPLS came into the picture. MPLS leverages both IP routing and SAF switching. MPLS is a forwarding mechanism in which packets are forwarded based on labels. MPLS was designed to support multiple layer 3. That is why we are calling it as a multi-protocol label switching. Typically, MPLS labels correspond to destination networks equivalent to traditional IP routing, right? SAF is mandatory for it. Without SAF, it is not possible to use MPLS. Now, benefits of MPLS. These are the benefits of MPLS. MPLS supports multiple applications, including you can use it for unicast traffic. You can use it for multicast IP routing as well. You can use it for unicast IP routing. Along with that, you can also use it for multicast IP routing. Apart from that, you can configure VPN, and you can configure two types of VPN: layer 2 and layer 3. Traffic engineering, TE, traffic engineering, which you are not gonna do cover over here. Quality of service, of course we will go for that. Atom, any transport over MPLS, any transport over MPLS, that is also called layer 2 VPN, right? So Atom is also there. MPLS decreases forwarding overhead on core routers. Of course, it decreases forwarding overhead because previously they were required to open 20 bytes long information, but this time they were required to open only 4 bytes long information. Second, previously they were required to store a complete internet routing table, but this time they will not require a complete internet routing table, right? Next, MPLS can support forwarding of non-IP protocols as well. Yes, it can support forwarding of non-IP protocols as well, such as ARP, CDP, STP, everything, right? That is part of layer 2 VPN actually. Now, in routers, you know very well that we have two things: control plane and routing plane. Sorry, control plane and data plane, right? Control plane and data plane, as I told you during Cisco Express Forwarding, CEF. So on all devices you will find all these, these two things: control plane and data plane. You know very well, routing protocols are handled by control plane, RIB is maintained by control plane, whereas FIB, which is also called SAF table, is controlled by data plane or will reside in data plane, right? And of course, whenever packet will come in, it will perform lookup in its data, in its FIB only, and accordingly it will take a decision, right? But in MPLS, there would be two things: LIB and LFIB. In MPLS, there will be two things now: LIB, label information base, label information base, and another one is called LFIB, label forwarding information base, right? So remember, LIB resides in control plane. It is same as RIB, right? Control plane, whereas LFIB will be in data plane. Right? To maintain LIB, like to maintain RIB, some routing protocols were required. Is not it? Routing protocols were responsible to maintain or to create RIB, right? Similarly, for LIB, label information base, there must be some protocols which will be responsible to create this LIB, right? So for that purpose, we will be having two things, either, two protocols are there or will be there in MPLS. One is called LDP, another one is called TDP. TDP is now obsolete technology. It's a legacy technology and it was Cisco proprietary. This TDP, tag distribution protocol, whereas LDP is label distribution protocol, So LDP will work something like routing protocols. Like routing protocols are responsible to exchange routes in between devices. Similarly, LDP will be responsible to exchange labels in between devices, right? LDP is for label distribution protocol. Right? So we will be using here LDP and MPLS throughout the this training, right? We will never go for TDP because TDP is Tag Distribution Protocol, which is Cisco proprietary protocol, and that's the only, that's the biggest difference in between TDP and LDP. Fine. So we will learn only and only LDP in MPLS now. Now, do you remember fib and rib? Like rib was in control plane and fib was in data plane. Similarly, lib, label information base, is in control plane. LFIB, label forwarding information base, is in data plane. Fine. I will show you all these things, right? But these terminologies are in MPLS only, right? And you should be familiar with them. Then there is a terminology that is called LSR or LSRs, label, switch, routers. Label, switch, routers. Right? You will be having two types of LSRs. One is LSR only, another one is Edge LSR. Again, there are two specifications in LSR, right? One is simple LSR, label switch router, and Edge LSR is also there. Label switch router. The only difference between Edge LSR and LSR is that LSR will be having all interfaces in MPLS domain. LSR will be having its all interfaces in MPLS domain, whereas Edge LSR will be having some interfaces in MPLS domain and some interfaces in non-MPLS domain. In other words, you can say that LSR will be responsible to switch your data based on labels only. Based on labels only. So remember, LSRs will be responsible to switch your data based on labels only, whereas Edge LSR will be responsible to take packet from non-MPLS domain without label, but whenever they will forward those packets towards MPLS domain, they will create a label and will append onto your packet, and then will forward that packet towards MPLS domain. And if they receive any labeled packet from MPLS domain and they want to forward that packet out from the MPLS domain, then they have to remove. Right? Hello. Fine. So this is the difference between LSR and SLSR. So you can see LSR, a device that implements label distribution procedure and primarily forwards packets based on labels only. SLSR, on the edge of an MPLS domain that implements label distribution procedure, forwards packet based on labels and primarily insert labels on packet or remove label for non-MPLS devices. So it can insert label as well as it can remove label. It will be depending on the flow of the packets, right? If packets are coming into the MPLS domain, then it will insert labels. If packets are going out from the MPLS domain towards non-MPLS domain, then it will be responsible to remove packets, right? So this is the difference between LSR and SLSR. Fine. You can also call them as PE and P router. SLSR is also known as PE, provider edge, SLSR, right? And LSR is also known as P router, that is called provider router, right? And then after, label switch routers, I have already gone through it. Fine. SLSR is done. MPLS example, as I told you, label swapping, right? They will generate some labels over there. Fine. This is summary. Then next is MPLS labels and label stack. Now we have to go through that. What is this label actually? We are talking about this from last 1 hour, that okay, MPLS will be forwarding traffic, forwarding data based on labels only. So what is that label exactly, right? So you see that label is you see MPLS labels, 4 byte long identifiers used for forwarding decisions. Like previously, we were using 20 bytes long IP header for forwarding decisions, right? But this time in MPLS, we will be using 4 bytes long identifier or 4 bytes long extra information for forwarding decision, right? Define destination and services for a packet. This label will be responsible to define destination as well as services for the packets, or for a packet, you can say, right? Then identify a forwarding equivalence class, FEC. It will be responsible to identify a forwarding equivalence class, right? FEC. FEC is a group of all those packets which have to be forwarded over the same path with same treatment. One label represents one FEC, and the label will be allocated to a prefix, right? Not to a IP, right? So whenever packets will be forwarded towards that particular prefix, they will follow a same path and they will go with same treatment. So one label will be representing one FEC, forwarding equivalence class.
Treatment means policy, equivalence policy.
Something like that. Traffic engineering, right? VPN, everything. So FEC, forwarding equivalence class, I will show you that what is the meaning by FEC over here. See, FEC is a group of packets forwarded in the same manner over the same path with the same forwarding treatment. And MPLS forwarding is what? Connection oriented. It's not connection less, right? It's a connection oriented. So I'll let you know that why do we call it connection oriented, because MPLS will be using TCP, LDP will be using TCP, because MPLS is nothing. It's all about LDP, label distribution protocol, right? Like dynamic routing is nothing. Dynamic routing is nothing. Ultimately, ICRP is doing work, right? So similarly, LDP will be doing work for MPLS. So I was telling you that MPLS label is a 4 bytes long identifier which is responsible to define the destination and services for a packet and identify a FEC, forwarding equivalence class. Have local significance. Of course, it has local significance. As I told you that labels will be having local significance, because all devices will be generating labels for each prefix according to themselves. Each LSR independently maps a label to an FEC in a label binding, right? Yes. I told you, one FEC, one label, right? That's the meaning by each LSR, right? LSR is what? Label switch router, whether it is SLSR or LSR, right? They will be responsible to generate labels, right? And also they will be responsible to map those labels to FEC, forwarding equivalence class, right? Or you can say they will be responsible to map labels to prefixes. Each LSR independently maps a label to an FEC in a label binding. Yes, label binding are exchanged between LSRs. Like if I have done some binding, right? Then I'll give that information to my neighbor. Just I explained to you, right? Like for an example, it is having okay, I told you before in MPLS that this is the lane of the router 1, and whenever router 1 will be generate any label for that directly connected prefix, it will be giving that binding to its neighbor that for this prefix, this is your outgoing label. You understand? Just give me 1 second, please. I'm sorry. So this is MPLS label. MPLS label is a 4-byte fixed length, locally significant identifier that is used by network core devices to make forwarding decisions for a packet. Labels define the destination and services for each packet and identify a forwarding equivalence class. The label put on a particular packet represents the fact to which the packet is assigned. Right? Forget about it now. Fact is done. This is your label format. This is your 4 bytes. This is the information contained by this label. In 4 bytes, it is having 20 bits for label number. First 20 bits are for label number 0 to 19. Right? 0 to 19. Experimental bits 20 to 22. Means 3 bits would be used for experimental bits. It is something like toss field in IP header. Do you remember that for toss we were having 8 bits inside IP header? Similarly, we are having these 3 bits in MPLS for experiment, and these bits are known as experimental bits, and these bits will be used for quality of service. These 3 experimental bits will be used for quality of service. Then S, this is only 1 bit. This is only 1 bit. Fine. So this is your label, right? So it is a 4 bytes long label, and first 20 bits are for label number. Next 3 bits are for experimental bits. S bit is 1 bit only, and this is called bottom of stack bit. Bottom of. See, in MPLS, it's not like that. It is gonna to keep only one label onto your packet. It can have multiple labels too. That's called label stack. Like it can have a group of labels, right, on a single packet. It will be depending on that which services of MPLS you are utilizing now. If you are using multiple services at same time in MPLS, then you will be using multiple labels over there, right? Onto IP header, onto your packet, you will be adding multiple labels. That's called label stack. So basically this S bit, bottom of stack, this bit will be responsible to tell a device that whether this label is the last label in label stack or some more labels are to be followed. See, of course it must be having this information whether this is the last label and then after IP header will start, or there are some more labels after this label, right? Because it can have label stack. So that's why its name is bottom of stack bit. Bottom of stack. Bottom label of stack. Bottom label in group of labels. Last label in group of labels. So it will tell that. Right? And last 8 bits would be used for TTL, and it is just used to prevent from indefinite loops. It is just used to prevent from indefinite loops. Same as IP header. Understood? So total 32 bits are there. You see, bottom of stack bit. If it is 1, which means this is the last label, and then after IP header will start, right? If it is 0, which means some more labels are there, right? So it is also possible to have multiple labels in between IP header and layer 2 header, in between layer 2 and layer 3 header, something like this. You see, MPLS can be implemented into 2 modes: frame mode MPLS and cell mode MPLS. Cell mode MPLS will be implemented over ATM only. So here we are not going to implement this cell mode MPLS, right? We will be using frame mode MPLS only. and you see it will work in this manner. You see, this is this is the way in which MPLS works actually. This is your packet, normal packet, like layer 2 header, layer 3 header, and then payload. But after label assignment, like whenever packet will insert into MPLS domain, a label will be assigned to your packet, right? And it will be assigned in between layer 2 and layer 3 header, and that is also called shim header. And you can have multiple labels in between layer 2 and layer 3 header, right? You can have multiple labels in between layer 2 and layer 3 header. Label stack, you see, usually only one label is assigned to a packet, but multiple labels in a label stack are supported. These scenarios may produce more than one label. Like if you are implementing these scenarios, then you can have multiple labels. Usually only one label will be attached to your packet, right? But if you are using following scenarios, then you can require to add multiple labels in between layer 2 and layer 3 header. Like if you are implementing MPLS VPN, then at least 2 labels will be there, right? If you are implementing MPLS VPN, then at least 2 labels will be there. If you are using MPLS traffic engineering, then again 2 or more labels, right? And if you are implementing VPN plus traffic engineering both together, then 3+ labels. You can see that. MPLS VPN plus MPLS traffic engineering. If you are using combination of both of them, right, then at least 3 labels will be there, and you can have more than 3 labels as well in between layer 2 and layer 3 headers. So if you are having multiple labels, that is called label stack. And then S bit, bottom of stack bit, will be responsible to tell whether this is the last label before IP header or some more labels are there before IP header. If it is 1, which means this is the last label. If it is 0, means that some more labels are to be followed. So there are some labels called like LDP label, VPN label, traffic engineering label, which is also called T label, right? So you will be calling them something like this. You see, you can have multiple labels. Like this is your layer 2 header, frame header, and this is your IP header, layer 3 header. In between you are having multiple labels like traffic engineering label, LDP label, VPN label, right? So you know, just the label which is just after your layer 2 header is called outer label. Is called outer label, and all other labels will be known as inner label, or also you can call them top, middle, bottom. Top, this T label will be top. I mean, just after layer 2 header, whatever you are having will be called as top label. Then middle label, then inner label or bottom label. In this way. See, top, middle, bottom. So top label and middle label are having S bit as 0, whereas bottom label is having its S bit as 1, because this is the last label in this label stack. Understand? So you can have multiple labels in a label stack. Now there are some protocol IDs which are used by layer 2 headers. Do you remember some, like we were having type field inside Ethernet header, and that type field was responsible to tell that to which protocol you have to hand over this packet, right, this payload. Like if it for ARP it was different, for IPv4 it was different, for IPv6 it was different. Similarly, if you are using MPLS, then it has to hand over it to the MPLS, right? So if it is unlabeled IP packet, which means if you are not using MPLS, if there is no label, then type field will be having 0x800, right? It is the older one that you learned during CCN and CCNP as well, right? If you are having MPLS running in your network, then that Ethernet header will be having 0x8847 in its type field, right, for unicast packet. But in case if it is multicast packet, then it will be having 0x8848. This is for MPLS, right? So for unicast packet it will be different, for multicast packet it will be different. Labeled, which means, see, what is the meaning by unlabeled IP packet? Which means IP header. It is not having any label over there, right? Labeled IP unicast, which means it is a unicast packet, but label is there. Labeled IP multicast, which means this is a multicast packet, but label is there. I hope that's fine. You see, MPLS, what are MPLS operations? MPLS label operations. An LSR can perform these functions: insert, swap, removing. Of course, it has to do. Of course, LSR, as I told you before, that LSR will be responsible to inject a label while packet will be entering into your MPLS domain from non-MPLS domain. And of course, it will be removing. That is also called popping. It will be popping label from the IP packet, from your packet, while packet will be going into non-MPLS domain from MPLS domain. Swapping will be performed by LSR. Only LSR, like is coming with this label number, will be forwarded out from this interface with this label number. That is called swapping. So remember, insertion and removal can be performed by as LSR, whereas swapping will be done by LSR only. Right? Now there are some rules. There are some rules, and these rules are that if a router is receiving packet with label, if router receives a packet with label, then it will always perform lookup in its LFIB, and LFIB resides in its data plane. Fine. So I'm again repeating, if any router receives a labeled packet, which means it is receiving packet with the MPLS label, right? So it will perform lookup in its LFIB. But in case if it is receiving, this is for labeled packet, for unlabeled FIB. There is a rule. So you have to remember, you have to memorize this rule, that if routers will receive labeled packet, then they will perform lookup in their LFIB, and if a router receives a packet, unlabeled packet actually, then they will perform lookup in their FIB. This is the thumb rule for MPLS. And do you understand the meaning by labeled and unlabeled packet? Labeled packet, which is containing label in that, unlabeled, which is not containing label in that. That is the meaning by labeled and unlabeled. Right? Fine. So in this way it works, as I told you before, that see, this is the router received one packet for 10.1.1.1. It added this label, forwarded it towards this, added this label. It is performing swapping, right? It is performing insertion, it is performing swapping, and it is performing popping. In this way it is working, right? Fine. This is done now. Next is identify MPLS applications. Forget about it. We don't need to go for this chapter now. They are just talking about traffic engineering and the VPNs and all. Forget about them. We don't need to go for that. See, this is what label assignment and distribution. So I told you, for label assignment and distribution, we will be using two protocols, either LDP or TDP. TDP is a Cisco proprietary, right? Proprietary protocol, whereas LDP is an open standard protocol, right? So basically we will be going through now LDP, right? So LDP will be responsible to form lib as well as alfib, right? So discovering LDP neighbors. Of course, the label distribution protocol is there, which uses TCP port number. You can see here that it will be using TCP port number and UDP port number 646. It uses both actually, TCP as well as UDP. For different tasks, it will be using different transport layer protocol. I'll let you know that for what it will be using TCP and for what it will be using UDP, but port number is common for both of them, right? Whether it is using TCP at transport layer or it is using UDP at transport layer. I hope that you people have understood it till now, right? So LDP is same as like BGP or other routing protocols like OSPF and EICRP and all, right? So like over there, EICRP was responsible to exchange routing information. Over here, this LDP will be responsible to exchange label information. So for that purpose, we will be implementing here LDP, label distribution protocols. So see, LDP establishes a session in 2 steps. Like hello messages are periodically sent on all MPLS enabled interfaces, same as OSPF. Like once you enable OSPF onto an interface, it starts sending hello packets out from that interface, right? Same is in EICRP, right? MPLS enabled routers respond to receive hello by attempting to establish session with the source of the hello message, right? So first of all, they will send hellos to each other, and to sending hello messages, they will be using a multicast address 224.0.0.2, which is for all routers, right? See, the meaning of this multicast address, that is 224.0.0.2, is for all routers, right? If you are sending anything with using this multicast address, which means that you are sending this message to all routers, right? Are you getting my point? See, this is, this multicast address is not used by MPLS only. This multicast address is used by multiple applications, like HSRP also uses this same address, right? Even if you are using IGMP, then also it will be using same multicast address, right? So there are so many things, there are so many protocols which will be using the same multicast address. So whenever you will require to send any packet towards all routers, you will be sending you will be multicasting with using this multicast address. That means it is for all. TCP is used to establish the session, right? And it will be using TCP and UDP both with and port number will be 646. So you have to remember it, right? Because in T-shoot they can do one thing, they can filter this port number 646 so that your LDP peering will never come up, right? Same as BGP. Like if someone have blocked port number 179, then of course BGP peering will never come up. Tell me, any problem? Sure. So this is all about MPLS, right? And today we will stop this class now, right? That was the introduction of MPLS actually, and tomorrow I will start doing implementation of this LDP, and we'll learn this LDP in more details, and I will show you that okay, this is the way that MPLS works actually, right? And then after I will start your VRF, virtual router and forwarding. First of all, we just need to go through the basics of the MPLS, and then I will start your VRF, virtual router and forwarding. In that we are having 2 things. One, VRF Lite. So first of all, we will cover VRF Lite, and then we will go for VPN, right? So do one thing,